Logarithmic functions. Okay, in previous video lectures, we've talked about exponential functions. We're now going to begin a series of video lectures talking about their inverse functions, which are the logarithmic functions or the log functions. Our objective in this video lecture is fairly simple. We want to change exponential statements or equations to logarithmic statements or equations and vice versa. What do we know? We know coming into this lecture what an exponential function is. An exponential function is a function of the form f of x equals c times a to the x. All right, pay particular attention. An exponential function has a variable in the exponent. The key to the exponential function that we want to focus on for today's purposes, or for this video lecture's purposes, is that exponential functions are one-to-one. And we know that when functions are one-to-one, that means they have an inverse. An inverse is a function or an operation that undoes the original function or operation. So exponential functions have an inverse, a function that undoes them. The inverse function that undoes the exponential function is called the logarithmic function, excuse me, or the log function. A lot easier to say log as opposed to logarithmic. All right, a couple things about the logarithmic function we want to talk about here. Let me spin my paper up a little bit. A logarithm is a name for an exponent. That's what a log is. A log is equal to an exponent. It answers the question, how many of one number do we need to multiply to get another number? So here's an example. 2 to the x is equal to 8. So, how many times do we need to multiply 2 to get 8? As I'm sure you know mentally, 3 times 2 to the third power is 8. All right, so how many of this number do we need to multiply to get this number? The log will tell us that. The log allows us to get at the exponent's answer. 2 is a base, so we have log base 2 of 8 is equal to the exponent. The logarithm tells us the exponent. All right, so the base raised to the exponent equals 8. Here's the base, here's the exponent, and then there's the 8. In the general case, and we'll give some vocabulary to you, a to the x equals y. All right, we want to get at this. How many times do we need to multiply a to get y? Okay, so the log base a of y is equal to x, which is the exponent. In this form down here, vocabulary, a is the base, which is nice because a is the base here in the exponential form. A, which is a little bit lower below the line that has the log and the y in it. The number or the expression in parentheses after the base is called the argument. And as I mentioned up here, a logarithm is an exponent. So a logarithm is an exponent. This is the exponent. So notice how we just switch these two things. A to the x equals y is the same as log base a of y equals x. Let's do some converting. Let's just make use of that and do some converting. Okay, so again, I'll put it up here. A to the x equals y. Whoops, a little bit too high. okay, is the same thing as log base A of y equals x. The log is an exponent. So here we want to convert each exponential equation to its equivalent logarithmic equation. Well, here's an exponential equation. Base of 5, exponent of 8 equals t. Let's rewrite this as a logarithmic equation. Log, okay, a is the base. The base goes slightly below everything, like a subscript that would be called. Okay, next comes the argument, and the log is equal to an exponent. So the log is equal to the exponent. The exponent is 8. Let's do this one. Okay, let's convert this exponential equation to its equivalent logarithmic equation. Log base. This is a base of 12. So this is a base of x in the exponential equation. So the base goes down here. This is the argument. So it goes inside the parentheses. -2 is an exponent, and the log is an exponent, so it goes on the other side of the equal sign. Let's take a look at this one. E to the x is equal to 10. All right, so we're going to put it into log forms. The base is e in the exponential equation, so it's base e. 10 is the argument. A log is an exponent. X is the exponent. Now there's something about here. We know that E, we saw in a previous video lecture, E is the natural base. Because we often find E, the number E, in nature. So we can, oftentimes, you can write it like this, log base E, because it gets used very often, okay, there's a special way to write a log base E. So log base E is equal to the natural log. I should say, let me put an argument in here. Log base E of x is equal to the natural log of x. And we just kind of know when we put natural log that there's an E down there. We just don't write it. Okay, so log base E of x is the same as the natural log of x. And let's take a look at your calculator for just a moment at a couple of things. Again, here's your E button. It's a second character above the division sign on the T84. Here's your log key. And here is your natural log key, which is base E. Okay, so there's some 3 keys, and we'll look at a couple of others in just a moment. All right, let's go the opposite direction. Let's convert from the logarithmic equation to its equivalent exponential equation. So here I have log base A of y. I'm going to rewrite this up at the top here so we have it as x. And one of the ways I like to do it here is I like to kind of go like this. It kind of helps me, I don't know, just something I was taught way back when. It kind of helps me keep it straight. So this again is equivalent to the base of a raised to the x as an exponent in this case is equal to the argument y. So I do draw kind of a start with a base and then do I guess a counterclockwise circle, a to the x equals y. So let's convert these logarithmic equations to their equivalent exponential equations. All right, y is equal to log base 2 of 21. Okay, so let's see. The base, 2 is the base, 2. Log is an exponent, so this is the exponent y is equal to the argument. Example 2 here, log base x of 12 is equal to 6. Again, log is equal to an exponent. This is the base. And if you want to, this is my little mental mnemonic here. X to the 6th base to the exponent equals the argument. And we have that. Let's up here a little bit. Let's take a look at this one. Okay, log base 2 of 10 is equal to a. Write that as an equivalent exponential equation. 2 is the base, a is the exponent, and 10 is the argument. Finally, we saw the natural log. Natural log of x equals to 4. Well, we know that natural log has a base of e. We just don't write it. There's an e right there. Okay, this is an exponent, so e to the 4th is equal to the argument, which in this case is x. Okay, finally, let's use our calculator to do some calculations for us, and you can see how this works. These all have different bases. Your calculator has an option here. If you look, let me get this up here so you can see it all. I think I've got it all in there. I think so. If you look down here, this log key down here, when I press log, notice it doesn't show a base. This key is for the common log, what's called the common log, which is base 10. So you don't have to write the 10 because it assumes there's a 10 base when you just write the log with no base. Okay, I'm going to clear that. And again, here's that natural log, which we know has a base of e. Again, we don't write it. It's just assumed, it's just known to be there. If you go into your one of your sub-menus, it's the green button and then F2. On my calculator, you'll see number 5 coming down here. I can put in any log base I want. So I'm going to choose number 5 because this has a base of 3. And I'll press enter. And now I can calculate what is the log base 3 of 81. In other words, how many times must I multiply 3 to get 81? All right, so 380. Remember, the log gives me the exponent. And I get enter. 4. Log base 3 of 81 is 4. I have to multiply 3 4 times. 3 times 3 times 3 times 3 to get 81. 3 times 3 being 9, times 3, 27, times 3, 81. Okay, let's do this one, example 6 over here. I'll come back to here again. And again, notice I don't have a base of 10, so I'm going to go back to my second F2 and choose option 5 on my calculator so I can put in my own base. The base here is 2. The argument is 1/8. I'll put it as a fraction just to make it look a little bit, so it looks the same. Okay, so how many times must I multiply 2 to get 1/8? And the answer is -3. I multiplied 2 -3 times, and I come up with 1/8. Okay, let's do this one mentally if we could. And then we'll check with the calculator. Log base 5 of 1. How many times must I multiply 5 by itself to get 1? Or thinking about it, 5 to what power is equal to 1? Okay, give that some thought. Take a number. What's the only power it can be raised to give you a result of 1? Hopefully you're getting the answer of 0. Anything to the 0 power is 1. Again, let's take a look. So I'll go back to my green F2. I'll choose option 5. I want the base of 5, but I want an argument of 1. Okay, there you go. How many times must I multiply 5 by itself? 0 times to get 1. That's 0. Okay, here's the base of 1/3. All right, I can do that. Again, green F2. I'll choose my log with my base I can put in. I'll put 1/3 in here. I might even put it in as a fraction. Sure enough, log base 1/3 of 27. And -3. Oh, I got the same answer again. That's interesting. -3. So the exponent 1/3 to the -3. Remember, this tells me 1/3 to the negative 3 exponent, base to exponent equals argument, equals 27. Let's take a look at that. Let's check that. So 1/3 raised to the negative 3. I should get 27 out of that, and indeed I do. Finally, natural log of 4. Okay, again, natural log. I'll do this in two ways, I believe. You can use the natural log key, which is, I'll raise this up a little bit here. Remember, the natural log key is here next to the 4. Okay, so I'm going to do this as natural log, which is automatically gives it a base of e of 4, and out comes 1.386 approximately to the nearest thousandth. If you wanted to, and this should work, I haven't tested it, but I'll test it now. Let's go back to that log base, and let's choose the base of e. Now remember, the e is above the division symbol, so I'm going to choose the e for the base of e and put 4 in here, and I better get the same thing because these are the same things. And sure enough, I get the same answer. So there you have it. Logarithms and their exponential equations back and forth. In our next video lecture, we're going to talk about the domain of the logarithmic functions.